Hello, everyone. I'm Situ Yao from Cornell. Thanks for coming to my talk. Today, I'm going to talk about compositional security for smart contracts. This talk is based on joint work with Ethan Chagatti, Haobin Ni, and Andrew Myers. Smart contracts run in an environment of unprecedented hostility. Several features of smart contracts make them more exploitable than others. They usually manage highly valuable assets, so attackers have a direct financial incentive to find and exploit vulnerabilities. The code and executions are public, which means attackers can observe and study their targets closely for free. What's more, smart contracts are open to anyone to interact. Thus, potential attackers all around the world can join easily at any time, and smart contracts might need to interact with unknown code and parties they don't fully trust. Therefore, it's not surprising that several vulnerabilities in smart contracts have already caused significant financial losses. According to a report from CipherTrace, more than $1.2 billion was estimated to be stolen or lost in just the first quarter of 2019. Consequently, there is a pressing need for better tools to understand smart contract vulnerabilities and to build and reason about secure smart contracts. People already identified many kinds of smart contract vulnerabilities, such as reentrancy attacks, access control failures, arithmetic errors, front running, and so on. And we've already seen a blossoming of security research projects trying to solve one or some of these vulnerabilities. A variety of techniques were applied, such as formal verification, fuzzing, pattern matching, symbolic execution. Existing work has mostly focused on securing a single contract rather than one application. But many existing smart contract applications are built as a combination of multiple contracts. And two contracts securing isolation might make a buggy application. Uniswap Exchange is an application on Ethereum that spans two contracts. In April 2020, an attack stole 25 million from Uniswap Exchange, while the two contracts of Uniswap are secure in isolation. The attacker exploited a complex interaction between these two contracts. Because the above tools analyze security based on single contracts, none of them can prevent the Uniswap attack without putting overly conservative restriction on interactions. So today, I'll introduce a new approach to smart contract vulnerabilities that can overcome current limitation of existing work. To give you an example, let's say there is a smart contract managing a multi-user wallet. Here's a wallet with $310. It maintains a data structure balance map specifying how much money each one of its users stores. It also provides functions so user can deposit and withdraw money. And let's take a closer look at the function withdraw. It contains 4 steps. Suppose a user like Bob wants his $10 back, then Bob calls this function, and the wallet will first check if Bob has enough money. If so, the wallet sends the money to Bob and wait for confirmations. Once Bob confirmed it, the wallet updates accordingly. So now Bob has no money in this wallet. It looks all fine as expected. However, there's a bug in this function. Let's go back to step 3. The wallet sent $10 and waits for Bob's confirmation. But Bob notices the bug in this function and wants to do something evil. Instead of sending back the confirmation, it calls withdraw again, which invokes a new execution of withdraw. And because balance map has not been updated, the wallet thinks Bob has enough money. So the wallet sends $10 to Bob again. So Bob successfully gets $10 more. What's worse, because the wallet is waiting for confirmation again, Bob can call withdraw again. Bob can actually repeat this attack until it stores all money stored in the wallet. In fact, this example happened in real life. You may already recognize it. It is the famous DAO attack, and a lot of money was stolen because of a reentrancy vulnerability, just like this. We think this kind of reentrancy issues are about trust. In this example, the wallet trusted Bob to confirm immediately after receiving money. However, Bob violates it by calling back withdraw again instead. So we want to somehow track and analyze trust. To do so, we apply a language-based technique called information flow control, or IFC. Information flow control is often applied to protect confidentiality, but here we focus on integrity, since smart contracts are public. In information flow control, we label code and data to indicate trust relationship. The idea is that more trusted data can influence less trusted data, but not vice versa. In other words, IFC prevents untrusted parties from influencing trusted parties. Let's look back at the example and see how we apply information flow control to it. The wallet trusts its own data and code, so we label them as trusted. Bob, however, could behave maliciously, so we label it as untrusted. Then this reentrancy started as Bob, it calls withdraw, then withdraw calls to Bob, and Bob called back to withdraw again. You can see there is a pattern indicating a reentrancy here. And let's take a closer look. See, this is the pattern of trusted followed by untrusted followed by trusted. This pattern is what we use to define reentrancy. More formally, we define a notion of L reentrancy from an integrity level L as an execution stack with two computations trusted by integrity level L, separated by an untrusted computation. So in the DAO example, there are two levels, untrusted and trusted. The reentrancy we just saw would be called T reentrancy for the trust label T. Definition avoid contract boundaries by defining it based on integrity levels. Comparing to existing work, because they focus on single contracts, which leads to contract reentrancy. Our definition, L reentrancy, is based on integrity levels, not contract boundaries. Suppose there is an application composed by two contracts, and one of them calls to an untrusted contract, which then calls to the other trusted contract. Consider T reentrant because both contracts in this application are in the same integrity level T, and it got called back to this T level. But it is not considered a contract reentrant because there's no calling back to any contract. On the other hand, if there is a single contract application that contains some trusted functions and some untrusted functions, and one trusted function calls to an untrusted external function, which then calls back to an untrusted function in this application. This execution is actually safe because we don't need to protect untrusted data. It is not considered T reentrant because there's no such a pattern as trusted calling untrusted calling trusted. But this is considered contract reentrant because there is a contract being re-entered. So L reentrancy gives us a clean and compositional semantic definition of reentrancy. Then the next question is, what kind of reentrancy is secure? Intuitively speaking, we think a reentrancy is secure if it does not create actual potential effects. If we can make sure that all effects on trusted data are also possible without a reentrancy, then a developer can safely ignore possible reentrancy when analyzing its program's correctness. We enforce this notion of security by locking integrity. We lock integrity when entering trusted code. And we prevent from re-granting locked integrity later. For example, when an untrusted party calls to a trusted function, we grant this integrity and lock this integrity level. The untrusted want to call back to another trusted function, it is re-granting this trusted integrity level, and therefore will be blocked. Please notice that only locked integrity level will be protected. Calling to other integrity levels is okay. There are two different strategies to enforce this kind of integrity locks. We can enforce it statically with a type system, or we can enforce them dynamically at runtime. The static lock brings no runtime cost, and it can detect errors before deployment of code. But unfortunately, it cannot handle unknown or legacy code that may not provide the same guarantees. And we know we need to handle that because smart contracts need to interact with unknown code. On the other hand, using dynamic lock, we need to pay high runtime cost, and it might result in potential runtime errors. But dynamic lock do support unknown code. So there is a trade-off here. We do need good performance, but we also need to be flexible. As a result, our strategy is to lock statically by default and lock dynamically on demand. Let's see how we can fix the DAO. So in the DAO's original code, by calling in withdraw function, we already granted the integrity level of trusted. And our type system cannot make sure this second step won't call any other trust operations. So it won't type check to prevent re-granting trusted integrity from happening. This is good because it is saying this program is vulnerable and we need to fix it. If the programmer really wants to send money, then a dynamic lock could be put. This lock will prevent any calling back to this trust function at runtime, so it will compile. So you can see with the help of logs, we get a secure DAO. This result is published earlier this year on Auckland, where we designed a core calculus called Serif. It defines compositional integrity-based reentrancy and also reentrancy security. It enforces reentrancy security with logs. It puts static logs when possible, dynamic logs when needed. And in the paper, we also implemented a prototype type checker as a proof of concept. Serif is a core calculus. It provides a great theoretical foundation, but it is not a practical programming language. We implemented a type checker, but not a compiler. And we didn't discuss how the runtime system look like concretely. Now we are working on designing and implementing a practical language called Skiff. Skiff is based on Serif. It aims to compile Skiff programs into code that can run on Ethereum. And now I'll mainly talk about challenges in implementing Skiff's runtime system. What do we need at runtime? One big challenge is to support dynamic trust management, not only because we need it as a foundation of our dynamic logs, but also because we think in real-world blockchains, trust relationships are dynamic. A contract's trustees can change over time. At runtime, we need to answer trust queries. We also need to support modifications over trust relationships. More formally, we want to support the following operations at runtime: if trust, set trust, and revoke trust. We need to answer a query about trust between contracts, and we also need to support a contract to add or revoke its direct trust to other contracts. In fact, how this runtime system is implemented is loosely coupled with our language, as long as it supports these operations correctly. And we've explored several different strategies to support such operations. Here we present a centralized strategy. Suppose there is a contract hub. All contracts trust hub to maintain trust information for them, and the queries, modifications are all sent to this hub. In this strategy, hub knows all direct trust over contracts. In other words, it knows the trust graph, like the figure on the right side. Notice that all contracts trust hub. To answer a question, knowing only direct trust is not enough because trust relation is transitive. So to answer a query, hub needs to say if it can find a path between the two contracts. For example, if A asks if it trusts C, the hub needs to do path searching. It finds a path from A to B, then to E, then to C. It finds a path, then it returns yes. This hub knows the direct trust graph. It can apply advanced algorithm to maintain a dynamic transitive closure of this graph and get a significant speed up on responding queries. However, this strategy requires all contracts to trust this contract hub. And this introduces additional trust, and it suffers from single point of failure. So we also designed a decentralized strategy to get rid of this additional trust, but that also brings drawbacks, such as worse performance. Next, our runtime system needs to support dynamic logs. At runtime, a contract needs to check if an integrity level is locked. It may also lock or unlock integrity levels to permit flexible reentrancy. We can also create a hub to maintain logs in a centralized fashion. And similarly, all contracts send queries and modification to this hub. To answer a lock query, the hub has no need to maintain a transitive closure. It can simply check if there's any locked integrity level trusted by L. So we've showed an example of how we can implement this runtime system. You can also implement it in any other ways if you don't like this centralized fashion. But please notice that this hub is put on chain, so you can actually check its code for its correctness by yourself. So as a conclusion, I introduced Skiff, a smart contract language based on Serif, providing compositional reentrancy security. And we talked about Skiff's runtime system managing dynamic trust and dynamic logs. Skiff can handle reentrancy attacks. More than that, because Skiff applies information flow control attacks techniques, it is able to naturally handle many other integrity failures and trust failures. And many important smart contract vulnerabilities are also integrity failures or trust failures through the lens of IFC. So I believe SCIF can be extended to handle more smart contract issues, such as confused deputy attacks. And in the future, we look forward to improve it. So hopefully, programmers can write more secure smart contracts. That's it. Thanks.